Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry Made Easy. In this second video on acid-base titration calculations, we're going to be looking at taking data from a burette as a titre reading, and then also at some more complicated acid-base titration calculations. So when you take a titration and do it accurately, you're using two pieces of equipment. You're using the burette to measure one of the components, whether it be the acid or the alkali, and then you're using a pipette to measure the other components that is then placed in the conical flask. The pipette gives a fixed volume. It is usually 25 centimeters cubed. Whereas the burette is a bit like an upside down measuring cylinder, where 0 starts at the top and then goes all the way to usually 50 centimeters cubed. And this allows you to have any volume between these two values. You can get larger burettes and smaller burettes. Reading the burette, you are given two values, and the difference in those two values is what we call your titre. Now, when reading both the final and the initial on the burette, you are looking for the meniscus. The meniscus is a phenomenon with liquids where at the top of the surface, it clings on by intermolecular forces, and then we're always reading at the bottom of the curve here, shown in blue. With a burette, as we said earlier, it's kind of like an upside down measuring cylinder. So 0 starts here, going to 1 to 2. So this one here, okay, is not 1.4. Instead, it's 0.6. You can see a burette is graduated in divisions of 0.1 centimeter cubed each time. As with all non-digital devices, we record all the figures that are known. So here we could definitely work out this is 0.6. But then we also add an extra digit to make 2 decimal places, which is estimated. And this extra digit can be 0 or 5. So here our first decimal place is 6. So we're going to have to estimate the second decimal place. With this estimated being 0, that's if the meniscus is pretty much on the line of the initial first decimal place. So you can see here that meniscus is directly on the 0.6 line. So we are going to estimate that we have a 0 here. If you find that meniscus is about halfway in between, as for this one here, then you would estimate it as being 5. So this one here, reading it, we know it's going in this direction. The value for this would be 23.15. because the meniscus line isn't close enough for it to be 23.20. What I'd like you to do is pause the video here and see if you can read off the initial and final readings of Titration 2 and Titration 3. Okay, for Titration 2, you should have got the following readings. This second one here, 46, is referring to the big line here, so it's actually 45.95. Again, because the meniscus is about halfway. So, getting into the habit of always being identify the known and then making an estimation of 0 or 5. So your trailing number here cannot be anything different than 0 and 5. Once you've taken these measurements of the initial and the final, then the difference in here is known as the titre value. And that's the volume that actually was released into the conical flask by the burette. So for example, if we had acid in the burette, that would be the volume of acid used in our titration to neutralize the alkali, which would have been in the conical flask. In the lab, what would happen is you would complete a grid like this, using the initial and the final readings for each titration. First, before you did a proper titration, titration 1, 2, and 3, which is shown here, you would run a trial run just to work out where the point of neutralization is. Because it's inaccurate, being a rough indication of this endpoint, we don't use this in any calculations. Real accurate titrations are definitely collected and used. You should always fill out, whether you're doing a PAG or in an exam, to 2 decimal places, with that trailing last decimal place being a 0 or a 5. Stated before, to work out the titre, which is the difference used or the volume used in the titration, you do final minus initial. Having done this, you're then going to work out the mean titre or the mean volume that you added. Now it's really important to only use titre values to work out this mean that are concordant. Concordant titres are within 0.1 centimetre cubed of one another. So, if you look at our data set here, titration run 1 and 3 are both within 0.1 centimetre cubed of each other and are just within that limit, so we could use them to work out the mean titre. However, 22.8 is too far, so we cannot use this to work out the mean titre. Take those values and divide by the number of readings that are concordant. That will give you your mean titre that you would use in calculations for the amount of volume you added to neutralise. Important when carrying out a PAG or looking at an exam question that you are looking for concordant titres within 0.1 centimetre cubed. Okay, with this extra bit of information about concordant results and mean titres, what I'd like you to do is attempt this question here. What I'd like you to do now is to pause the video and have a go at working out this answer. Okay, so first of all, let's think about how we're going to approach this using our 6-step calculation strategy. From the previous video, we know that our strategy looks like so, and that actually we don't really have to do step 4, rearranging equations, because we're going to use our grid. Now our grid, in terms of the format of known and unknown, looks like so. If you calculated this correctly, you would have worked out the concentration of sulfuric acid, our unknown, is 0.166 to 3 significant figures. And if you've done that, then you followed this correctly. If you didn't get that, we're going to quickly go through this walkthrough using this 6-step approach. So first of all, let's box the value we're trying to work out and underline the given values. We've been asked to work out the concentration of sulfuric acid, so that must be our unknown. Given values. With this volume and concentration of sodium hydrogen carbonate being given, we know that we have 2 pieces of information that must be the known. Now, an extra thing here, we have boxed and we've underlined the given values in the question here. However, there is information locked into the data here, and that is the volume of the sulfuric acid. Remember, we're looking for concordant results to work out a mean titre. So concordant results are within 0.1 centimetre cubed of one another, and you can see all of these values here for titrations 1, 2 and 3, which are the accurate titrations that can be used. Remember, the trial run cannot be used, are within 0.1 centimetre cubed of each other. So we're going to take these 3 readings, divide by 3 to get our mean titre. That concludes the bug element of our strategy. Already got ahead of ourselves. We've got the grid format for the equations that we need, MVC. Next, we just need to check the units of any given values. Now, all these units of volume are in centimetres cubed, but we know that our concentrations are going to be expressed as moles per decimeters cubed, so we need to convert centimetre cubed into decimeters. Just convert that 25 centimetre cubed, and then we've also got to convert the 15.10. As we've stated before, we don't need to rearrange the equation because we're going to use the grid to guide us through to the right answer. But what we are going to do is substitute in the values now that we've got them in the correct format. And then we're left with the calculation side. So we're going to follow A, B and C in that order. The number of moles is volume times concentration. So we're going to take those 2 values, and when we do that multiplication we get 0.005. We're going to turn our attention to the balanced symbol equation in order to work out molar ratio. So it takes 2 moles of sodium hydrogen carbonate to react with 1 mole of sulfuric acid. It allows us to work out the moles of the unknown because a 2-to-1 ratio requires us to divide this by 2. So we do the same process to this value here. This is that value. Then we've got N and V, so we can work out concentration, which is our end game, as we boxed that earlier, and that is going to be moles divided by volume using the triangle N equals VC. And so if we take those 2 values, we get the answer of 0.1655. But of course, if we look at our actual calculation here, the values we're given, some are given to a higher number of significant figures. For example, we've got 4 significant figures here, 4 significant figures here, but our lowest is 3 significant figures. So we need to convert this into appropriate significant figures, which is 0.166. So that's our answer in moles per decimeter cubed. Okay, the final exam question we're going to have a look at in this video is the following. So pause the video here and have a go. Okay, if you got the answer of 2.21 moles per decimeter cubed, then that's full 4 marks out of 4. If you didn't, we're going to go through the process now. First of all, we're going to work out what we need to find out by boxing that and then underlining any given values. So the question's asking us for the concentration of the original ethanoic acid. Box that, and then we start to process what are the values that we've been given. So obviously, with the information that we've been given, there's quite a lot of volumes for the ethanoic acid. The first two here are all to do with how we've taken a 10 centimeter cube sample from the bottle. These more complicated versions of titrations or any calculation, it's very good to do pictorial representation of what is going on to get your head around what all this information and data looks like. Place that into a container such as a conical flask, which now has 10 centimeter cubed of the original vinegar. And then what's happened is that's been diluted, make up a 250 centimeter cubed solution of the original 10 centimeter cubed vinegar plus 240 centimeter cubed of water. I have to come back to this later because this is going to allow us to use the C1V1 C2V2 equation, where C1 is the original from the bottle of vinegar, so this would have been C1, but the 10 centimeter cubed is also C1 because it's not changed at this stage. The volume V1 is 10 centimeters cubed, and then our new concentration is of this 250 centimeter cube sample, of which the volume for that V2 is 250 altogether. If any of this is unfamiliar, make sure you go back and watch the video on dilutions and solution calculations titled C1V1 equals C2V2, as it's a really important skill to have in these more difficult multi-structured calculations. This, then the 25.45 centimeters cube, was then used in the burette. What we've done here is part 2. We've been starting to write the equations. Our first equation is the C1V1, C2V2 equation, and our second equation comes from the fact that we're doing a titration of the ethanoic acid with barium hydroxide. And so we're just going to fill out our grid of known and unknown. The third step here is to then convert any of the values into the correct units. And so really, we're only focusing on the given values for the titration element of this. So that's going to be the volume here, because that was used in the titration, and also the volume of the barium hydroxide used in the titration. At this stage, what we're going to do is then put this into our equation. What makes this question more difficult is that you have to substitute the correct values at the correct time. So at the moment, we're just focusing on the titration results. So we're going to put in the values for that. Labeling up in this bug section of a strategy is really important because it makes it easier to transfer the correct values into the correct strategies. Now, having selected these, we're just going to clean up these annotations because they're getting quite busy. In the exam, be as messy as you want, as long as you're tracking it and not getting yourself confused. And in the sixth step, we're going to calculate the concentration of the unknown ethanoic acid in our titration. Okay, so what we're going to do is first of all work out the number of moles of the known barium hydroxide. N is V times C, so we're going to do this value times this value. We're going to use the mole relationship in our balanced equation. It's 2 ethanoic acids to every 1 barium hydroxide. To go between the 1 and the 2, we need to multiply by 2, so we're going to do the same operation with this value. We're going to times that by 2. And with this N value, we can do C is N divided by V. So we're going to do this divided by this. We've got the concentration of the ethanoic acid in the titration. Now, This is where this little diagram helps you link it all together, because we took a sample here to titrate against, and that sample is exactly the same concentration as that you've discovered here. So basically, this value here is C2. So this sixth stage, the calculation, hasn't just finished yet. We've worked out C2 through our titration. It was a long-winded way of getting this value, but that's what we've got. We've got V2 here at 250 centimeters cubed, and our V1 is 10 centimeters cubed. As we're trying to work out C1, what we're going to do is use the equation C1 V1 equals C2 V2. And again, go back to the video if you need to for this. We're going to make C1 the term. So, and as we've talked about, as long as in these ratios or these scaling ratios, as long as the units are the same, we don't need them in decimeters cubed. So we're just going to input the values, because we've basically got to this bit, substitute values. We're just doing a second run through of this, just with this part. And if we do that, times by the 250, 10 centimeter cubed is our proper scaling. And if you work that out, you get 2.21. Final answer. So you can see how titration calculations can link to some of the dilution stuff we've been doing and be quite difficult. So key things are to follow the strategy. You may have to, depending on how many levels to the calculation there are, go through the strategy twice over. So we went once over to work out the titration concentration, and then we went through this kind of again in order to work out the concentration of the bottle of vinegar, our C1. Okay, hopefully you found this video useful. If you have, ensure that you like the video, and then ensure that you subscribe to the channel for new videos as and when they're uploaded.